Alrighty, so welcome to our 12th lecture for OCSP. My name is Sydney and I will be teaching today with Isabel. We're going to be learning today about solvents and solvolysis reactions. So let's go ahead and get started. So our learning objectives for this lecture, we're going to be first talking about the classifications of different solvents. As you can see, we have 3 different groups to talk about. And then lastly, we're going to talk about solvolysis reactions and have a few examples. So there are, as I mentioned a moment ago, 3 different groups for classifying solvents. We have Bronsted-Protic versus aprotic, Lewis donor versus non-donor, and then we have polar versus apolar. And we're going to go ahead and define each of those. So our first group to talk about is the Bronsted-Polar group versus, Bronsted-Protic versus aprotic group. The thing to know about this group of solvents is that they have acidic hydrogens, and an acidic hydrogen is a hydrogen connected to any electronegative atom, such as F, O, or N. Hello. Electronegative atom. And F, O, and N are the most common examples. And because these solvents have these acidic hydrogens that are connected to an electronegative atom and have that partial positive charge, they're going to be good participants in hydrogen bonding. So when I say that something is a hydrogen bond donor, I mean that it gives a hydrogen in a hydrogen bond. You might remember hydrogen bonding from Chem 2070 as a very important interaction between atoms and molecules. And then some example solvents include water, as well as alcohols such as methanol, and acids such as carboxylic acid. If you look at the molecules for each of these examples, you'll notice that they all have that hydrogen that's connected to an atom such as F, O, or N. And actually in each of these 3 examples, that atom is oxygen. So I drew out an example of a hydrogen bond, just in case some people didn't remember from Chem 2070. Basically over here on the left, we have a water molecule, and we have this acidic hydrogen that I have highlighted in blue. This acidic hydrogen is going to have a partial positive charge because it is connected to the electronegative atom that has a partial negative charge. These blue dashes right here represent the interaction between this acidic hydrogen and the lone pair on this oxygen in another water molecule. So this oxygen is partially negatively charged as well. There's this intermolecular hydrogen bond going on and they attract each other. This water molecule would be referred to as the hydrogen bond donor because it's giving a hydrogen, while this water molecule would be called the hydrogen bond acceptor because it's got the lone pair on the oxygen right here. And then something else to know about protic solvents is that they can stabilize anions or other charged molecules. So I have an example of what that type of stabilization interaction looks like. We have 4 different generic alcohols drawn here. If you didn't know, the R group just stands for rest of molecule. So here's the alcohol group, and then this is the rest of the molecule. And then this X with a negative charge, that just stands for any electronegative atom. And so we have our electronegative atom, and we've got our alcohols that are acting as the solvents. And just as in our example before, each of the hydrogens in the alcohol is going to have a partial positive charge, while each of the oxygens are going to have a partial negative charge. And then these little dashes, they represent the interactions between the solvent molecule and between the electronegative atom. Now, depending on the identity of the electronegative atom, they can be either dipole-dipole interactions or hydrogen bonds. So if the electronegative atom is an F, O, or N, it could be a hydrogen bond because as we've seen before, it would be very similar to what's drawn in our example here. We would just have like a partial negatively charged oxygen, our electronegative atom, and then like the rest of the alcohol group. However, let's suppose that our electronegative atom here is not F, O, or N, but another electronegative atom, such as the halogen. In this case, it would be a dipole-dipole interaction between the electronegative atom and the hydrogen. Either way, these interactions, either dipole-dipole or hydrogen between the electronegative atom and the alcohol group, they stabilize this electronegative, negatively charged atom. Solvation is the term that we use to refer to these stabilizing interactions between a molecule and a solvent. And you're going to hear that word solvation a lot as we talk about solvents. Now that we've talked about what it means to be a protic solvent, the definition of an aprotic solvent is just the opposite. They do not have acidic hydrogens, and thus they cannot act as hydrogen bond donors. Are there any questions about protic or aprotic solvents before we move on? I'm going to take that as a no. So I'm going to move on to our next classification group, which is Lewis donor versus non-donor. And here is where definitions get tricky because you just saw on the other page where I talked about hydrogen bond donors. Well, here, when we're thinking about donors in terms of a solvent, we're referring to specifically donor of electrons. And not donor of a hydrogen to a hydrogen bond. So I made sure to draw up the little definition here so that you don't get confused and that I don't get confused. Anyhow, a donor solvent is a molecule that has an electronegative atom, such as oxygen or nitrogen, that can donate unshared electron pairs and act as a Lewis base. So some good examples of a donor solvent include ether, which if you didn't know was just generically ROR. And we can see that there's that oxygen there with its 2 lone pairs. We have THF, which looks kind of like hexane, except it has an oxygen right here. And then we have H2O and other alcohols, which, as you probably remember, also have an oxygen that can have unshared electron pairs that act as Lewis bases. Now, as you might remember, H2O and alcohols were some of our examples from the last the last solvent classification, which was protic solvents. They're listed here. Solvents can be in more than one category. So water and alcohol would be considered protic donor solvents. And there will be a really nice diagram a few slides later where we'll talk more about how all these solvents are like related together. So don't worry about that too much for now. I just wanted to bring it up. Now, Lewis donor solvents can participate in H bonding just like the protic solvents can. But because they have that unshared electron pair, they're not donating the hydrogen. So I've drawn examples showing how THF could hydrogen bond if there's another water molecule in solution as well. Similarly to before, we have our oxygen with a partial negative charge. Our hydrogen bond is represented by these dashes here, and then we have a partial positive charge on the hydrogen in the water molecule. Because THF doesn't have a hydrogen connected to an electronegative atom, it's not going to be able to hydrogen bond with itself. However, molecules like water and alcohol that do have both that oxygen with the unshared electron pairs and a hydrogen connected to an electronegative atom, they're going to be able to hydrogen bond with themselves. So that's just something to keep in mind. But THF can only hydrogen bond with another type of molecule. Now, non-donor solvents are the exact opposite of donor solvents. They can't act as Lewis bases. And some examples include alkanes, benzene, anything that does not have a lone pair on an electronegative atom. Are there any questions about Lewis donor versus non-donor solvents?
Did you say alkanes or alkenes?
Alkanes.
Okay, thank you.
Yeah, absolutely. Any other questions? Alrighty, we're going to go ahead and move on to our final group, which is polar versus nonpolar solvents. So this one is defined by the dielectric constant that we will explain in a moment. Just as a heads up, I'm going to be going pretty in depth into like the background of what it means to be a polar solvent and like the background of the dielectric constant. You're not going to have to use all this information like as you do your day-to-day problems, either in this course or 3570, but I felt like it was important to talk about what exactly these solvents are. So polar solvents have a dielectric constant that is greater than or equal to 15, and nonpolar solvents have a dielectric constant that is less than 15. And I'm sure by now you're wondering, since I've said it several times, what on earth is a dielectric constant? Well, the dielectric constant is the interaction energy between two charges with respect to energy. And it measures how easy it is to separate the charge. Now, if you've ever taken physics, I'm sure you've probably seen this equation in some form. E stands for the interaction energy between two charges. And then we have this highlighted epsilon, and this stands for the dielectric constant. This R stands for radius, or the distance between the two charges. And then we have our K constant up here, and we have two different charges right here, which are represented by Q1 and Q2. Now, before anybody gets concerned, we're not actually going to be using this equation. Like, we're not going to give you problems where you have to like plug in the value, exactly what E is or exactly what epsilon is. However, I was just showing this equation because it demonstrates how these different variables are related to each other. That's all. Spelled epsilon wrong, so I'm going to fix that right now. Epsilon. There we go. So as you might notice from this equation, the interaction energy and epsilon, the dielectric constant, are inversely related. When one of these is big, the other one must be super small, and vice versa. So let's think about this in terms of solvents. We know that polar solvents have a pretty big epsilon value. So if we have a big E, we know that they also must have a low interaction energy. This means that there are weak attractive and repulsive forces, which are those interactions, which means that charges can be separated. When I say attractive and repulsive forces, I'm sure you probably know that when you have, let's say, two like charges, if we were to bring them together in a polar solvent, they would be very weakly repulsed. And let's say that we had a positive charge and a negative charge. In a polar solvent, they would be weakly attracted. Basically, the punchline is that oppositely charged ions associate less in polar solvents than in apolar solvents. And that's the, I guess, main takeaway from this portion of the lecture. Okay, so now that we've talked about the dielectric constant a little bit, let's think about how we classify polar solvents. So it's important to note that all polar solvents consist on molecules that have a dipole. So basically, in order to be a polar solvent, you have to have a dipole. However, not all molecules with a dipole are necessarily polar. So I've drawn two examples here. I've highlighted the C to O dipole in blue. Right here on the left, we have this molecule right here, and its epsilon value happens to be 6.1. If you remember from a slide ago, in order to be polar, you have to have an epsilon value that's greater than 59. I'm sorry, greater than 15. So this molecule, by that definition, is apolar, even though it has a dipole. And we're not going to get into the exactly what about the molecule causes it to have this epsilon value. Just what's important is that its epsilon value is 6.1, so it's apolar, which fortunately is a lot simpler than using this equation or anything like that. Now we have this molecule on the right, looks kind of similar. However, its epsilon value is 59, which is a lot greater than 15, so it's going to be polar. So I know that we've discussed a lot of content. This is the end of our review of the 3 different classifications for solvents. Are there any questions that I can answer? Alrighty, I don't hear anybody saying anything. So I'm going to go ahead and move on to our nice little summary of what we've just talked about. This chart was drawn by the students who taught this lecture last year, and they did a really great job. We'll talk a little bit more about what exactly you should remember and like know off the top of your head, but just now, don't think that you have to memorize like the entire chart like right now, but it's definitely something that you might want to bookmark to look at later. So on our first sheet of the chart, we have all of the polar solvents, and as you might remember from a slide ago, they're the ones that have the epsilon value that is greater than or equal to 15. So I talked a little bit about how solvents can fall into more than one category. Here we have our protic solvents, or I'm sorry, our polar protic solvents. And if you remember, the protic solvents are the ones that have the acidic hydrogen and participate in hydrogen bonding. So over here, we have some examples that I discussed earlier, water, alcohols, and you'll notice that some of these are also donors, meaning that they have a free lone pair and can act as a Lewis base. So just keep that in mind. Again, a lot of solvents fall into multiple categories. And polar protic solvents have excellent both cation and anion solvation, which again, solvation is just that those interactions that I drew earlier on the protic solvent page. So now we have the polar aprotic solvents. These are polar molecules that do not have an acidic hydrogen and thus cannot participate in hydrogen bonding. These are some common examples down here: DMSO, HMPA, DMF. They have excellent cation stabilization, but no negative, good grief, no anion solvation. And then here are just some diagrams of what the molecules look like. I would say that the polar solvents definitely show up more in the reactions, and I would recommend trying to commit some of the examples for like a polar protic solvent and a polar aprotic solvent to memory, just because those do show up a lot, as you'll see within the next couple of lectures. So lastly, we are going to talk about the nonpolar solvents, and these ones have an epsilon value that is less than 15. So over here on the left, we have our protic donors that are nonpolar. So these are nonpolar molecules that have an acidic hydrogen and participate in hydrogen bonding, but they also have that lone pair that is on an electronegative atom that can act as a Lewis base. And then we have some examples over here of protic donor solvents that are nonpolar. As you can see, the epsilon values are both kind of low. And then they have moderate cation and anion solvation. Lastly, over here, we have the nonpolar aprotic solvents, which can be either donors or non-donors. And we have examples here. Basically, the non-donors, they don't do any solvation at all, while the donors, which have that lone pair that can act as a Lewis base, they have moderate cation solvation, but no anion solvation. So again, the nonpolar solvents in terms of reactions for 3570 generally show up less, I would recommend getting pretty familiar with some examples for protic and aprotic polar solvents. Are there any questions about anything we've discussed before I hand things over to Isabel? Alrighty, I don't see anybody raising their hand or hear anybody speaking out. So I'm going to pass things over to Isabel.
Let me just share screen. Do you see that?
Yep, looks good.
Perfect. Hi guys, my name is Isabel and I'm usually a study group leader, but today I will be teaching you about Solvolysis reactions. So just to get started, we're mostly going to be talking about E1 and SN1 reactions, and these reaction mechanisms are similar to what you've already seen. But to define solvolysis, it's the reaction of an alkyl halide with a solvent where no other base or nucleophile has been added. And you'll see how that applies through examples that we're going to do. So first, we're going to do the solvolysis of tert-butyl bromide, and we're going to walk through the SN1 mechanism. So in case you guys are unfamiliar with tert-butyl bromide, I'll draw it up here. It looks like this. Or you can write it out like this. And that's just what tert-butyl bromide is. So the first thing that we're going to do, because we know that it's an SN1 mechanism, is you have to undergo carbocation formation. So I'll write that right here. Let me restart that. So again, we have tert-butyl bromide. And our first step is that the Br is going to act as a leaving group. And this is done in equilibrium. We'll get back to that in a few seconds. But what we're left with is a positive charge on this carbon, and our bromine is floating in solution. So for SN1 reactions, the first step is always the rate determining step. And in this case, that happens to be carbocation formation. So right here, I'll write RDS. And the reason that carbocation formation is the rate determining step is because carbocations are typically difficult to form. So carbons prefer to remain in an octet and not be charged. And that's why you see that the larger arrow in the equilibrium is pushing towards the tert-butyl bromide, because again, carbon doesn't want to be charged and would rather be in the octet. So now that we have our carbocation, we're going to introduce a solvent. So I'll just draw it down here. So we have this here. And our solvent that we're going to be using today is ethanol. So I'll write it like this. Another way that you can write ethanol, and I'll do it up here, I'll say ethanol also looks like this. And solvents are just what you use to carry out the reaction in. In this case, ethanol is a polar protic solvent, so I'll write that right here. And we know that it's protic because the hydrogen is still attached. If it was just OET with a negative charge on the oxygen, then it would be polar aprotic. And remember that our bromine is still floating in solution. But what's going to happen now, let me move the charge over a bit, or I'll draw this bigger for better visualization. The Lone pairs on the oxygen are going to attack the positively charged carbon, and that's going to form a covalent bond. And remember how I said that carbons prefer to remain neutral, which they have 4 groups attached to them, which is why our bigger arrow is now pushing towards the right. And what we have is the ethanol attached. And now because oxygen has 3 groups attached to it and 1 lone pair, we can expect a positive charge on the oxygen. And that is unfavorable. So we want to get rid of the positive charge on the oxygen. And we do this by deprotonation. And we use the solvent to deprotonate as well, because that's the only other molecule present in solution. So in the carbocation intermediate, the bromine is also essentially being substituted for the solvent. So now that we added the ethanol and we underwent carbocation formation, now we're going to undergo deprotonation. So now I'll just redraw our product from the last step. And what we can expect to happen is that another molecule of ethanol is going to come in, because remember, it's in solution. And the lone pair is now going to attack the hydrogen coming off of the oxygen. And the electrons in that bond are just going to go back onto the oxygen. And this is the product that we end up with. And this can also be written as CH3, 3C, OE2. And remember that now we still have other products in solution, which is the ethanol, the protonated ethanol with the positive charge, and we still have our Br. But this is the main product that we're looking for right here. Does anyone have any questions about solvolysis using the SN1 mechanism? All righty, then we're going to move on to solvolysis with an E1 mechanism. And here we're still going to be using terbutyl bromide so that you guys are familiar with how to do both of the mechanisms with similar molecules. It just depends what you have. So the first step again is still carbocation formation. So I'll just walk through that again in case you have some trouble with it. So remember that the Br is going to act as a leaving group. And what we end up with is this carbocation and bromine in solution. And based on other E1 reactions that you've seen, you can anticipate the formation of an alkene because you're going to be removing a beta hydrogen. But I'll redraw this for better visualization, and we'll see how that mechanism happens. So now I'm going to redraw everything out with the carbons and the methyl groups themselves. So this is still the same carbocation that we just formed. I just drew it out. And you'll see that for the methyl group on the bottom, I drew out the bonds between the carbons and the hydrogens. In this case, it doesn't matter which methyl group you choose because they're all the same in relation to the central charged carbon, and they would all yield the same product. So now what's going to happen is we're still going to have our ethanol solvent. But now, instead of attacking the charged carbon, it's going to attack the beta hydrogen that's coming off of the beta carbon. So it's going to go here. And this double bond, this bond between that carbon and hydrogen is going to go here to create a double bond and stabilize this positive charge on this carbon. So we're essentially just creating the carbon-carbon double bond to stabilize the charged carbon. And what we end up with is this. And in case anyone is having trouble seeing where everything basically came into play from the reactant to the product, you can think of this methyl group as being here. Oops. Then this one remains here. And where we got the double bond from, that's from this carbon right here. So now it's left as a CH2 because of the double bond. And again, the solvent reacts with the beta hydrogen to form the alkene. And don't forget that what's still left in solution is again charged, protonated and charged ethanol and bromine, because that was our leading group. Does anyone have any questions on the E1 mechanism? Alrighty, so now we're going to move on to competing reactions. And when you have tert-butyl bromide in a polar protic solvent, both E1 and SN1 reactions can compete with each other in solution. And solvents are a big determiner in the type of reactions that take place, but there's two things that have an even larger influence, and that's the alkyl structure and the nucleophile strength. And these just help to determine the type of reaction again. So you have 4 options between SN1, SN2, E1, and E2. So again, we're going to use our classic example of tert-butyl bromide and ethanol solvent. So we'll start with this. And here's our ethanol. And like I said before, we can expect both an elimination product and a substitution product. So first we could draw our elimination product that looks like this. And if you notice, there's 2 substituents coming off of the double bond. You can keep that in mind for later. We'll talk about that more in terms of major and minor isomers. But this would be your elimination product. And you also have a substitution product, which looks like this. And we just ran through both of these mechanisms. So in case you guys still have trouble seeing where we got both of these products from, we did them in the last 2 slides. So this would be good practice. And again, this is our substitution product. And remember that we're still left with ETOH2 in solution and Br. But when we say that there's competing reactions, we mean that one product might take precedent over the other product. So in this case, our elimination product is at 19%, and our substitution product is at 81%. So essentially, we're going to see a lot more of our substitution product than we would see in our elimination product. And we can walk through another example to see how you can form multiple products. Let me just make this smaller so I have more room. One second. Okay. So now we're going to go through a new example. And I'll draw out the molecule for good visualization. And now we have H2O and ethanol. And this is our solvent. And again, we can expect to form multiple products. So first we can focus on the elimination products. So we know that the Br is going to come off, and that's where the initial carbocation is going to form. So the two elimination products that you can expect, one is having the double bond here, and the other is having the double bond here. So like I said before about the substituents, in the first one, there's 2 substituents on the double bond. But in the second one, there's 4 substituents on the double bond. So we know that if you have 4 alkyl substituents, especially compared to 2, because there's more, the second one will be the major isomer. And this altogether constitutes the elimination products, which is at 62% in solution. Now we can also expect our substitution products. So the first one that we'll get is this. And the second one that we'll get is this. And this is, again, substitution at 38%. So we can see that in this case, the elimination products, there's more of the elimination products than the substitution products within this specific competing reaction. And in case you guys are wondering about the substitution products, the reason that we have both H2O and ethanol, or because we have both H2O and ethanol in solution, they're both competing for the charged carbon on the carbocation, which is why we see both of those substitution products. So right here is the OH and right here is the OET. And remember that you're also going to have to go through your deprotonation step. So although we started with H2O, that's going to add on, but we're going to have to deprotonate a hydrogen from that, which is why you only end up with OH. And the same thing with ethanol. It starts off with a hydrogen on it, but once it attaches, the oxygen is going to be charged. And remember that that's unfavorable. So you're going to want to deprotonate. Anyone have any questions on competing reactions? All right, so I'll move on to the last thing that we're talking about. So rearrangements are also possible for Solvolysis reactions. So I'll show you an example and then I'll walk you through it. So this is the molecule we're going to be working with. And I'll highlight the specific methyl group. And you'll see exactly why in a few seconds. So now our solvent, it's still ethanol, but we're also going to heat it. And what we're left with so now you see that the highlighted or colored methyl groups get rearranged and that our OET ended up over here. But we knew that because you have your chlorine right here, you would expect it to attack that carbon. And this is because of methyl shifts. So let's take a closer look into it to see what exactly a methyl shift is. Just put a line here. Okay. Actually, makes it easier. So our chlorine is going to come off because that's our leaving group. And that's where our carbocation formation step is. So the carbon that's currently charged is a secondary carbocation. When the positive charge is on this carbon, this is a secondary carbocation. So I'll circle it right here. But if we undergo a methyl shift, where you have this methyl coming here, what we're left with is a positive charge on this carbon, which would make this a tertiary carbocation. And that's what's preferred. So that's why we undergo a methyl shift. So now what we're going to see is that it's going to move over. It's going to be more stable this way. And this is where we see the rearrangement occur. And now that our positive charge is on, has shifted to form a more stable carbocation, our solvent is going to come back in, and it's ethanol in this case. And it's going to attack this positively charged carbon. And it's just going to attach itself. And we're just going to undergo a deprotonation step with another molecule of ethanol. So it's going to take this hydrogen. And the product that we end up with sorry that it's so tiny on the bottom. But this is essentially what we get. Does anyone have any questions on rearrangements? So now I'm just going to go over final points for SN1, E1, SN2, E2 reactions. And this has to do with polar solvents specifically. So remember that polar just means that there's a high dielectric constant, and that allows for the separation of ions. So polar protic solvents are best for SN1 and E1 reactions, and they have both cation and anion solvation. So they're able to stabilize the charged carbocation intermediates. And this is specifically because it's protic. And this is as opposed to polar aprotic solvents, which are best for SN2 and E2 reactions. These have no anion solvation, so they don't stabilize negatively charged nucleophiles. So polar protic solvents stabilize the nucleophile. But in SN2 and E2, you need a good nucleophile for the reaction to run. So you need an aprotic solvent so that the hydrogen bonds can't stabilize the nucleophile. So what you basically want is for the nucleophile to retain its strength in SN2 and E2 reactions. And the next slide is just a chart that puts it all together. So for example, you see with the methyl groups, only SN2 is able to occur. You can definitely look at this chart just to get a hand on what you think the reaction should be based on what you're already given in terms of the substrate and the solvent. So if you were to put this on like a flashcard and try to test yourself, this would definitely be a good study option. You don't necessarily have to memorize it, but it would be very good to know. Definitely, if you're taking 3570, like I would keep looking at this during the unit just to really familiarize yourself with it and understand why everything happens a certain way. But yeah. Does anyone have any questions for Sydney and I? I also got a question in the chat. How do you know it's 62% and 38%? That's not necessarily in the scope of like what we know. It's just like what we've been told through our lectures. I would love to know exactly why it is that way, but I'm not completely sure. Okay, Sydney, can we wrap it up? I don't think anyone has questions.
Yeah, so again, like we went a lot into the background for the topics for solvents and solvolysis reactions. Not all of this stuff is required to be memorized in depth. As you do your problems in study group, you'll start to learn how to apply the material and you'll get a better grasp for what actual parts are like, okay, this is something that maybe I should memorize, or this is something that I really should become very familiar with. And then you'll learn that some of the stuff that we presented is more like background information that, while still important, is not always as relevant for solving the common types of problems. And I'll stick around if anybody else has questions.
Thank you so much.
Thank you.